Hello, everyone. Welcome to today's Be Curious event. My name's Ritu Dand, and I'm the Chief Scientific Officer at Springer Nature, and it's an honor to host today's keynote speaker, Dr. Pushmeet Kohli, Head of AI for Science at DeepMind. I know he's an incredibly busy person, so I feel we're very lucky to have this opportunity. Thank you, Pushmeet, for making the time to join us. I also want to take this opportunity to thank our editorial board members for joining us. I'm going to start with a very brief summary of some of Springer Nature's interest in AI as researchers and editors. I think there are some exciting developments in this space which will be of interest to you. Next, we will hear from Dr. Pushmeet Kohli, and then that will be followed by a live Q&A for all of our audience. So before I begin, I've just got to get some housekeeping out of the way. You can ask a question at any point, whether you're logged in or not. And if you use the Q&A functionality to the right of your screen to type your questions, we'll take them at the end of the talk. And finally, I hope you're all aware that the session is being recorded. So there is no doubt that artificial intelligence has presented us with many opportunities as well as challenges in academic research. And more recently, with the announcement of ChatGPT, we've seen many column inches and Twitter characters dedicated to analyzing its potential impact. And from what I have seen, it appears to be a very powerful technology. And, you know, with ChatGPT doing everything from authoring papers to writing poems. Springer Nature has also been very heavily investing in technology and AI because we recognize that AI can better support some of our researchers and editors. And I'd like to take this opportunity, if I may, to share some of those examples of where we've seen some of the greatest benefit. So firstly, we've been trying to see how we can serve our researchers better by providing more accurate recommendations for further reading based on an author's search history or their reading preference. And we've seen a lot of success in that space. And for our authors, we have been using AI to auto-translate content to increase the accessibility and global reach of their research. We're well aware of how important it is for an author that the research is easily discoverable, and being able to easily translate it into several languages helps us to promote the work to a much wider audience. And you'll be pleased to hear that we've also been using AI to better support our editors. For example, we have been improving the accuracy of our peer review finder tool to suggest better and more accurate potential peer reviewers. And this is a space with a lot of continued development as AI capabilities advance. We've also investigated using AI for spotting fraudulent papers. And we have been able to use this to more effectively be able to detect aberrations. And this is really important to improve the integrity of research that is published. And as gatekeepers of the scientific literature, it's definitely something we will be looking to do more of. In addition, we have several exciting projects ongoing, which are still in the R&D phase, but I would love to be able to share some of those with you here now today. We've used AI to generate new text, which we have done for our machine-generated books program. And to date, we've published about 50 books, which has been fabulous. We're also converting text into something new, such as a research summary or a translation. And some of you will have seen examples of this posted by us on social media. And while that may not sound super exciting in an open access world, being able to have an accessible summary of all the research that's published would facilitate greater collaboration between communities and also allow the general public who support much core funded research to be able to share in this excitement that scientific research brings every day. And finally, and perhaps most excitingly, we are currently exploring whether there is a role for AI to query text to support editors in reviewing of their manuscripts. And in the wider world, we're already seeing evidence of how AI can help advance the pace of biomedical science and indeed the broader research field to better support society to address some of our most pressing global challenges. And our guest speaker today could not be better placed to help us give an understanding of this technology, which presents many exciting possibilities. As with all new technology, we as a society have a responsibility to carefully assess any new development. And as publishers, we are very aware of the limitations that this technology presents. And I think we're going to hear a little bit more around that in the talk later. And with that, that's all from me. I'm going to hand over to Dr. Pushmeet Kohli, Head of AI for Science at DeepMind. Pushmeet's research centers on AI to solve real-world but science-related problems, from genomics to structural biology and fusion to quantum chemistry. He was the lead investigator on AlphaFold, a state-of-the-art AI system that predicts the 3D structure of proteins, and that's what many of you are here to hear more about today. And we were delighted to have the opportunity and the privilege to work, to publish that work at Nature. Pushmeet will also talk about the power of AI to reason about complex concepts and push the boundaries of knowledge to accelerate the speed of science across all disciplines. Please give a warm welcome to Pushmeet. I think I can safely speak for everyone in this room. We're very excited to hear about your research and how it's being used to advance biomedical and other scientific research. Over to you.
Thanks, Ritu, and thanks Springer Nature for giving me this opportunity to talk about AI and the role we believe it will play in scientific discovery. So I have a few sort of slides, and the slides are now sort of available. So the title of my presentation is Using AI to Accelerate Scientific Discovery. And I'll be sort of talking about a number of different things in this talk, but I'll start by sort of covering the mission statement of DeepMind. I work at DeepMind, and this is a remarkable sort of organization which was founded just over a decade ago with this, some would say, very ambitious goal of solving intelligence to advance science and benefit humanity. And so what really is sort of important for in this mission statement is to first think about what do we mean by intelligence. And the second element is how do you really advance science? How do you advance science as and as a whole sort of field of study is about understanding the world that we live in, and would give us more agency about in controlling and having influence over the world. So it's a very important and motivating sort of mission, and I find it personally very meaningful. So coming to machine learning and AI, I mean, the analogy to sort of give in terms of what machine learning and AI provides us today is an ultimate general purpose tool to help us understand the world around us. So if you think about the Hubble telescope pictured here, it allowed us to think about and see the universe in very sort of minute details, things that we weren't able to see before. And I think machine learning and AI is providing us another sort of competency. It is it is giving us the ability to reason about the world and to make sense of the incredible amount of data that scientists all over the world are collecting about nature, about different fields of study, and how do we make sense of it all. Now, if we think about science in general, it's a very broad area. So the first question that you start from is, where do you start? I mean, science is so broad, and there's so many different disciplines, and there's so many impactful and important problems in science. Where should one start from thinking about where machine learning and AI can have the highest impact? So there are a number of criteria that we think about while thinking about this issue. The first is, does the problem have high scientific significance and impact? I mean, that's the whole sort of mission of the company. We want to make sure that AI and machine learning can be applied towards scientific breakthroughs that have the highest impact. Secondly, the whole research philosophy of DeepMind is to approach these problems in a multidisciplinary, collaborative, mission-focused way. And so that mission focus and that large collaborative approach requires the team to sort of think about a clear objective function in mind. So there is a clear objective function that you're optimizing against that allows everyone in the team to think about what is, in essence, the problem that needs to be solved, and what does success means for that problem to be solved. And finally, intelligence does not happen in a vacuum. Right? Intelligence does not happen without experience. We sort of gain knowledge in the world by interacting with the world. We need sort of that experience can be in the form of data, or can be in the form of sort of access to a simulator that can generate data about the problem and the domain that we are interested in. So these are the three key requirements for a scientific problem to be appropriate for machine learning. It should, we think about it as having high scientific significance and impact, having a clear objective function, and having lots of experience, either through the form of structured data that has been collected by the community, or sort of an accurate or efficient simulator of that domain. Another way to really talk about the problems that we look at is the fundamental nature of those problems. And this talks to the first point that I was talking about earlier, which is focus on impact. And this is where we focus on root node problems. So what are these root node problems? These are fundamental problems in different areas of science that if you somehow solve them, they unlock downstream progress on a number of different application areas. To give you sort of two examples, the first problem is the problem of protein folding. This is about understanding how do proteins fold, what is the structure of a specific protein. Now, if proteins are essentially the building blocks of all life. And if you somehow understand how do these proteins, what is their shape, how do they fold into the shape that they take, and what is their function, then that can unlock a lot more progress in understanding how biological systems behave. Can we understand diseases better? Sort of, can we design proteins to sort of for certain, to accomplish certain purposes, for synthetic biology, for drug discovery? In a similar sense, if you're looking at the problem of quantum chemistry, if you somehow are able to solve quantum chemistry completely, then that opens up implications for material design, for sort of designing high temperature superconductors, for designing better batteries, and so forth. So just to sort of now focus on one specific problem, and the project AlphaFold, which I will like to give an example of this approach. Let's get back to the protein folding problem for a moment. So what is the protein folding problem? Now, you and me, all of life, everything that is living today, like that we know of, is essentially made of proteins, right? We, like humans, we are essentially a large majority of what constitutes a human is just water. And the actual blocks that make us what we are, the fact that I'm talking to you, the fact that you're hearing this talk, that's all happening because of proteins interacting with each other, right? These are the building blocks, the Lego, the motors of the biological system, about every living object on this planet and beyond. Now, so what is a protein? It's essentially a sequence of amino acids, and the sequence of amino acids, when it takes up a specific structure, and this structure informs the function of that protein. Now, determining this structure takes years of experimental work, and a lot of work has been done by the biology community over the many sort of past decades in understanding structure of specific proteins, but still we know only a fraction of the structures of the protein. And finding the structure of all proteins by just knowing their amino acid sequence has been a 50-year-old grand challenge in biology. If we think about the importance of this problem, you can get an indication of it by the amount of effort that has been spent on evaluating progress on this problem. I would like to highlight the role of the critical assessment of protein structure prediction, which is the CASP assessment, which is an external independent benchmark that has been running since 1994 every 2 years. And it's like a gold standard for evaluating progress on this incredibly important and challenging problem. And so something to sort of mention about CASP, it's a completely blind assessment in the fact that what happens is biologists all over the world for a period of time contribute their predictions and structures that they have just recently found into a central repository, which no one has access to, only the organizers of this assessment. And then protein folding sort of teams across the world try to make predictions about these structures. And kudos to John Mould and the CASP organizers, who have done an incredible job in sort of setting up this incredibly important assessment program. And so, as I was saying, CASP has been running for more than a decade now. And if you look at the progress on protein structure prediction problem as evaluated by this completely blind assessment program, you see that there was some progress, but it was somewhat sort of reaching a point where the problem was far from being solved. And so the first time we entered, where DeepMind sort of entered this assessment in 2018 in the CASP, in the 13th version of the CASP assessment, we showed that machine learning can have a significant role in this problem by improving the accuracy by almost 50%. And then beyond that, but the problem was not solved there. And so we went back after that sort of result, which gave us confidence about the role of machine learning and AI. We went back, re-architected the whole sort of system, and produced AlphaFold 2, which allowed us to reach atomic accuracy as CASP 14. So just to give you a sense of what was the magnitude of the contribution in AlphaFold 2, if you look at the errors or the median RMSD, which is sort of a metric for measuring error in the predictions, you see AlphaFold has almost sort of 1/3 the error of all the other systems that had been submitted in CASP 14. And so, more remarkably, the error was under 1 angstrom, or it had reached atomic accuracy, and which sort of essentially meant that the CASP organizers declared that the structure prediction problem in this sort of form was essentially sort of solved. So just to give you a sort of qualitative sense of some of the predictions, here are 3 interesting proteins that we encountered. The ground truth structure of this protein, which has been experimentally, of these structures have been experimentally verified, are depicted in green, and the prediction of AlphaFold is in blue. And what you can see here across these 3 different types of proteins is that how closely the AlphaFold prediction matches the ground truth structure that had been obtained using experimental means. On the extreme left, you see the ORF8 protein from SARS-CoV-2. Now, of course, a number of us have seen the spike protein from SARS-CoV-2. It's essential in terms of mutations in the spike protein can cause changes in how the virus actually binds to the ACE2 receptor and so on. And so each of these proteins has sort of an important effect. And the study of these structures is extremely important to understand the behavior of the full sort of organism. And so even for SARS-CoV-2, we were able to get these structures very, very quickly at the start of the pandemic to sort of even were able to share this with the wider community to sort of inform what could be done there. And this gives you a hint as to the power and impact of this kind of technology. So not only did we sort of develop AlphaFold 2, but we open sourced it, and then we used it for finding the structure of almost every single protein that is known to scientists today, and deposited it in the AlphaFold protein structure database, which was built in collaboration with EMBL EPI, which is the European Bioinformatics Institute based in Cambridge. And this has, since the last sort of a couple of years, has become the standard tool in biology. This allows for free and completely unrestricted access to every structure and academic and commercial organization use of almost sort of 200 million sort of proteins from almost the entire protein universe, and has allowed us to reach every corner of the research community. And of course, this whole process, in which we shared this amazing sort of resource, was done in a collaboration with keeping in mind safety and ethics, where we consulted experts from across biology research, pharma, biosecurity, and human rights. So what has the impact of AlphaFold been so far? As I mentioned earlier, protein folding had the promise to support drug discovery, and that's what we are seeing. It is supporting antibiotic research, resistance research. It is accelerating drug discovery. It's even sort of helping scientists fight plastic pollution by developing new enzymes and giving us, shedding us more light into the fundamental structures in biology. For example, one of my personal sort of favorites is a result last year on modeling the nuclear core complex, which is a key component of how a cell and a sort of nucleus sort of operates. And so there are hundreds of other sort of papers and applications that have come out which have used AlphaFold, and it has been mentioned by sort of commentators as a true gift to humanity. Now, just to go and give you specific case studies on how AlphaFold has been used. So the University of Oxford has been working on malaria for many sort of years, and they have started using AlphaFold for this problem. And so they took AlphaFold to make a prediction of a specific protein, the PFS 4845 protein, which is associated with malaria. And AlphaFold was able to give researchers a very crisp structure for this protein that allowed them to think about which bits of the protein need to be incorporated in a vaccine. By using these insights and combining with other results, they are now sort of towards developing a sort of a vaccine candidate that they want to go forward and investigate. Now coming to a completely different use case, researchers in the Center for Enzyme Innovation in University of Portsmouth have been using AlphaFold to understand the structure of specific enzymes which break down plastic polymers. And knowing the structure of these enzymes can allow the development of efficient enzymes, which specifically are more efficient in decomposing these polymers. And so again, this is another sort of very important sort of application as we look at addressing some of the challenges that we face in the world today. So to give you a sort of a sense, a broad sense of how AlphaFold has been received by the community, it has been used by more than 1 million users, either sort of scientists, PhD students, experts from all over the world, from 190 countries, like 1 million sort of users, from 190 countries, more than 3 million sort of structures have been viewed. And the AlphaFold sort of paper has been cited, and the proteome, the database paper has been cited more than 9,000 sort of times. It was mentioned as the breakthrough of the year by Science. It was considered the method of the year for 2021 by Nature Methods, and across the board, it has had a huge sort of academic impact. But the role and importance of AI does not stop at AlphaFold or even at biology. We have been using machine learning and AI techniques to accelerate progress in a number of different areas. In the topic of quantum chemistry, we are modeling the electron density of materials. This was a result that was published in Science 2 years back. We have been controlling, we have trained the machine learning system to build reinforcement learning policies that can stabilize plasma in fusion reactors. This was a work that was done in collaboration with EPFL, the tokamak at EPFL, and was published by Nature last year. We have used machine learning models for accurate weather prediction, and even sort of use machine learning and AI models to come up with new mathematical conjectures that have connected different fields of topology in collaboration with mathematicians. So across the board, you can see the breadth of impact AI and machine learning can have in science. Now, with every powerful technology, and especially technology like AI and machine learning, which has incredibly broad potential, it needs to be sort of used responsibly. It's not a solution to all problems. Its use case needs to be considered carefully, and also it needs to be applied in a responsible fashion, considering the impact, the downstream impact it will have. And so this is something that we think um, we take very seriously. Another important element is really understanding AI's limitation. How we apply these tools matter as much as where we apply them. And so there is an element of the problem of problem specification, where you want to make sure that the machine learning AI system understands what is the right problem that we want to solve. And AI, again, is not a substitute for scientists. It's essentially a great tool. It's essentially an amplifier for what scientists are able to do. So that's, I think, the key sort of element. And with that, I'll conclude my talk, and thank you for listening.
Thank you. That was amazing for me. I mean, it was, it's so fantastic to hear about the potential and the way it's been used. We are waiting for questions, and while we wait, I'll start with, we've got one coming, I think. If AlphaFold is the first proof of AI's ability to solve complex problems previously thought unsolvable with current computing power, which scientific challenges are next in your sights?
Yeah, thanks. Thanks for the question. And I think, as I was sort of mentioning, AI is it's such a general purpose technology that I think all of science will be sort of impacted by it in some shape or form. To give a concrete sort of example, I was saying that proteins are like the building blocks, the Lego pieces of life. So if proteins are the Lego pieces, the ingredients of life, the DNA, our genome is like the recipe, right? It's like, how do you construct a living object, like a human, like a frog, like a virus, like a bacteria, right? It's like a recipe, and we don't understand how that recipe works. How is it that one single cell is able to contains all the information to create a whole organism? And how does it work? What happens if there are mutations? What happens? So the whole sort of recipe of life is one such problem. It's a very broad problem, but and a very sort of challenging problem. But I think, just to give you a concrete example, I think understanding the genome, understanding the recipe of life is one of the things that we are looking at.
So, I mean, did you just say that one day you hope to be able to make a human with AI, or am I putting words into your mouth?
I think you're putting words in my mouth. Like what I said is that nature is incredible. Nature is somehow able to create from a single cell, from a sort of an embryo. It is able to produce a living human, a baby, and the baby grows to a human, right? Do we understand the mechanics of that? We don't at the moment. We don't completely understand what is happening there. Like we know a lot, but we don't sort of understand the complete sort of picture there. And so one day, hopefully, we'll be able to understand and decipher nature, right?
Yeah.
Not to be able to sort of create sort of nature, but like we'll be able to sort of understand it.
No, I can absolutely see it, going from proteins to protein complexes, and then perhaps temporal expression, or whatever you want to do. I can see the step-by-step advance. And if I may ask you one more question, AI technology in this space is progressing really, really quickly. So how quickly do you think you're going to be able to recreate a cell rather than a human being?
I think the problem that AI sort of and machine learning looks at, it doesn't sort of talk about the problem of creation. It talks about the problem of understanding. So I think the question is how is I think the question to come back to the question that you asked, one could ask the question, how soon would you be able to understand a cell? And that's an incredibly interesting and important problem. Can you have a complete characterization of a cell? Do you understand when would a cell sort of divide? Can you understand how will the cell sort of react in this particular condition, right, or that particular condition? And I think that there is a lot of research that needs to be done in even sort of understanding what is a cell, how does it actually work, how does it behave in certain contexts.
I think it's absolutely fascinating, and I don't think I'm allowed to hog you anymore. There is another question coming, so let's start with that. What is the role of theory in the age of AI? What do you think would be the role of scientists in the future?
Yeah, I think these are two very interesting and important sort of questions. I think so. I think there are two key sort of roles as scientists, right? One is there's an element of, at the end of the day, as humans, we want to understand the world, right? AlphaFold, for instance, has an understanding of protein folding, but there's still sort of that transfer as to how can we make sense of that problem, right? That understanding piece, that communication piece. The humans will be still that key sort of communicator, the people who will be able to interpret what the AI and machine learning sort of finds, and that translation piece, right? To be able to sort of say, this is what is happening. And then there is another very important role is of alignment. So science is about understanding nature, but also science is about sort of doing things for the benefit of humanity. And so what do we want this understanding to be used for? That's another sort of the problem specification problem. What are the problems that as humanity we are interested in solving? And that, again, that is the role of scientists. The scientists will be able to sort of convey, this is really important for humanity. This is really important for scientists, right? So I think those two things will never go away. The role of understanding from a human perspective as to how nature operates, as well as sort of the role of specifying what are the problems that are needed for humanity, that we want to solve, that are important.
Yeah, no, I absolutely hear what you're saying. It's a little bit like when we sequence the genome, and we've got a very high resolution sequence of it all. And there were people saying that in the 90s, when they were first thinking about it, it'll be the end of molecular biology. Far from it. It's accelerated research in an amazing way. And the advances we've seen in the biomedical space are absolutely phenomenal. So, I mean, I absolutely know this is going to be one of the most exciting areas to come. And I do look forward to hearing more about how this area develops. So we've got the next question in. Can AI extrapolate? Oh, no, I've missed one. How good is AI at predicting the function of an unknown protein?
So if you so AlphaFold, I'll talk about AlphaFold. I'll answer this question from the context of AlphaFold 2, right? So what AlphaFold 2 does, it makes this prediction of a structure of a protein, and in fact, the protein is unknown. So like if you have sort of proteins, if you sort of put a sort of protein into AlphaFold 2 and ask a sort of a sequence of amino acids into AlphaFold 2 and ask it to predict the structure of that particular protein. Sometimes it can leverage template information, which is if there are nearby sort of proteins, similar sort of proteins in the past that people have sort of studied and there were structures, people then sort of normally use template-based methods where they said, well, I roughly know what the structure is. Maybe that can help me guide my prediction. AlphaFold 2, sort of not only AlphaFold 2 is good at these kinds of proteins, but it's sort of very good at quite novel proteins in the sense that proteins for which no templates exist or no similar sort of protein or its structure was known. And so for many of these proteins, AlphaFold was able to produce very, very sort of remarkably accurate sort of structures. And that comes back to the CASP assessment that I was mentioning, that you wouldn't know how good those structures are, but we know now because there was an independent assessment where where scientists sort of tested AlphaFold 2 on unknown proteins, which were supposedly unknown, right? Nobody in the world knew about them apart from these specific sort of people who had just determined the structure of these proteins experimentally. And AlphaFold 2 was remarkably accurate in some sort of places, doing the work that has been done over many, many years, right? So sort of there were sort of cases where a whole lab and a series of a number of scientists have been working on one specific protein over multiple years, and they were about to sort of publish a paper, and then they ran it over AlphaFold 2, and it also produced the same structure or a very similar structure. And in other places, what AlphaFold 2 was able to do is people had some data lying around in the lab, but they were not able to fit a structure that explained that data. So they used AlphaFold 2. The AlphaFold 2 sort of gave them a structure, and they can then by using a technique called molecular replacement, they actually could find the experimental structure by starting from AlphaFold 2's prediction. So they were sitting on this data for like many, many years, and then by using AlphaFold 2, they were able to unlock it.
So have you put many structural biologists out of a job?
No, I think that again we are sort of the question is how many structural, like the amount that the amount of work that structural biologists can do with AlphaFold 2 is has incredibly expanded. Like if you are a structural biologist, right? Earlier you were waiting on sort of an experimentally verified technique, and it would have taken some months or maybe in some cases years, and in some cases you didn't even have a option. Like in developing countries where you don't have access to some of these techniques, you were sort of just guessing, right? What could be the structure? And AlphaFold 2 has enabled to sort of accelerate structural biology, expanded structural biology, and sort of democratized and given access to a larger pool of scientists these kinds of tools.
Okay, we've got a sort of a tutorial type of question. How does one access the AlphaFold 2 protein structure database? Yeah, and so there is a second part before you continue because it's related. Is there a step-by-step guide to use AlphaFold 2 in public domain that researchers can use?
Yeah, so I think with AlphaFold 2, as I mentioned, we open sourced the AlphaFold 2 sort of model. So people can sort of use it in their own labs. And in fact, a number of different scientists across the world have built sort of their own interfaces based on that model. But still, that requires you to sort of know your structure, go into these models, and then find the structure. So what we have done with our partnership with EMBL EPI is provide this AlphaFold database. And this is like, you just go to that website. It's like the Google search for proteins or Google Maps for proteins. You just put your sequence into that into that page, and out comes your structure. So it's as easy as like a normal sort of search query.
That is truly amazing. That really is desktop biology, if I ever heard it. The next question's coming through. You mentioned that AI should be used with responsibility. How do you believe we can check an ethical usage of AI?
Yeah, so I think this is a very important question. Thanks for asking, and I think it is there is no sort of simple answer to this question. Sort of even the definition of what is ethical. I mean, it's something that is needs to be done thought about very carefully. In which context? What are the applications? So I think there are many places. First, what is the ethical sort of development? So for the first place is ethical development of an AI system. Then the ethical release of the AI system. And then the final thing is ethical use of the AI system, right? So there are all these different sort of elements there. And while sort of thinking about the AlphaFold to release process, I can again sort of think about, I can use AlphaFold as a case study, but actually this applies to many other problems in science that we are working on. So at the start of a project, when we are thinking about developing an AI system for science, we do ethics review, and a safety sort of review through our internal team, and we do sort of get feedback from experts, safety experts as well, domain experts working in this area about what can this system be used for, what are the good uses as well as what are the malicious sort of uses, so that we have a good understanding of this. Again, in the case of SARS-CoV-2, as I mentioned, right, we predicted the structure of the SARS-CoV-2 or fate protein, and then at that point of time, we asked structural biologists, what should we do with that structure, right? We sort of some of the key leading structural biologists, and they, after considering it, they advised us to sort of release it to the community, because the whole sort of world was working towards trying to understand the virus and trying to sort of make sense of how do you deal with it, right? So I think all these sort of elements of development of these systems, as well as how do you release them, and how do you use them for certain applications, ethics has to be at the center of all these different in all these different places.
I completely agree, and I think it's also a very it's a role that we as editors and publishers need to reinforce ourselves, ensure we are including ethicists as part of any peer review procedure on a new AI development. And move with due diligence and care, because we have a responsibility to society to do that diligence in the first instance. Questions are coming in fast and furiously. I have a follow-up question on predicting unknown proteins. The question was about the function of the protein. Yes, AlphaFold produces a structure, but can AI go further by predicting function?
Yeah, so I think that's again sort of on the question of function. Proteins, the function of a protein, there are different mechanisms and different things that proteins do, right? And there are a lot of things that need to be understood to think about to predict the function of a protein, right? For example, so now from a sequence you have the structure, but what other proteins this protein will bind to? Which small molecules or drug would this protein interact with? What would happen if there's a mutation in this protein? So those are sort of, all these are interesting and important topics that are currently AI and machine learning techniques are built on. And so already there is a lot of work that is happening on taking sort of the structure produced by AlphaFold and then and then trying to make and try to predict the function of that protein. So there are I think there are a number of methods that have been proposed in the community which already sort of do that. But still it's an active area of research. So I don't think this problem of predicting the function has been solved. It's not solved at all, but completely, but it is a very active area of research. And I think AI will have a big role to play in this particular problem.
And would you say the same for the different protein states, whether it's an active state or not? That's exactly the same sort of situation and problem.
Yeah, exactly. So I think I mentioned that this notion of intelligence, it does not happen in a vacuum. It sort of, the machine learning model is extracting this knowledge or this understanding from the data it sees. And if, for example, there are certain conformations of a protein that are really sort of much more prominent in the PDB, the protein database on which AlphaFold 2 was trained on, then those are the conformations that you will see in the predictions, right? So it's sort of, it does not. So there's an element of how do you explain all the different conformation states? How do you understand dynamics? How do you understand protein-protein interaction? These are all sort of interesting areas of further research that we at DeepMind, as well as other sort of research labs, are working on.
Exciting times. And linked to that question, do you think prediction by AI can reach the point that we can expect new functions or activities based on the mutations that spontaneously occur in proteins, and that can bring new and unexpected function?
Yeah, so I don't see a fundamental blocker to this competency. So this is a hard problem, and I think this is, at some point of time, I do think eventually this will be solved. Now, when it will be solved, I think there is uncertainty about that timeline, but I don't see fundamentally any sort of a blocker or any roadblock which says this cannot happen, that a machine learning system or AI system cannot solve this particular problem. It has the ability to reason about physics. It has the ability to sort of understand sort of evolutionary and biological sort of information. So like a sort of scientist, it is able to sort of extract and sort of leverage all the different insights from all these different disciplines and information sources to be able to reason about this problem. So I don't see there being a fundamental sort of a blocker to achieving this specific competency.
I thought you said there was a role for scientists in science.
Yeah, so I think the role of scientists is, I mean, the eventual sort of role for scientists is basically what is the problem that you want the machine learning system to solve, right? And also the role for scientists is basically to be able to understand what is, and I think I'm not saying that all these problems will be solved sort of tomorrow. I mean, there is still a role of scientists for actually helping and building these techniques. Like someone sort of asked me, well, the AlphaFold team, what is the composition of the AlphaFold team? Like, how many computer scientists do you have? How many engineers you have? How many structural biologists you have? And my answer to that question is, well, we might have started with X number of computer scientists, Y number of structural biologists, Z number of engineers. By the end of it, it was X plus Y plus Z of computer scientists, X plus Y plus Z number of structural biologists, X plus Y number of Z of engineers, right? So it's like total football, right? Everyone sort of really understands and works on this in a multidisciplinary sort of fashion. AlphaFold 2 was a creation of scientists.
Yeah, I just don't know how far it will remain the creation of scientists, but let's move on. Has AlphaFold 2 solved the protein folding problem fundamentally based on physical principles? If not, is there still value in that? Or are machine learning approaches showing us that we might be needing an overhaul in our concept of solving problems together?
Yeah, so I think the AlphaFold 2 sort of architecture, the machine learning architecture, and I think that one place where I think you introduced me as the lead investigator for AlphaFold 2. I was part of the team, but I think sort of John Jumper, it was sort of John Jumper and Demis Hassabis were the key sort of team leads for AlphaFold 2. So I don't want to sort of take too much credit for all of that work. But if you look at the very elegant design of AlphaFold 2 in its architecture, it was inspired from physics. It was sort of really inspired from a biophysical sort of viewpoint, that these other insights about the physics of the problem were baked into the machine learning model, which really helped it to crack the problem eventually. So yes, it is leveraging a lot of data. It's leveraging a lot of evolutionary information, but it's also leveraging a lot of insights that scientists have learned over time about the physics and chemistry of the problem.
Thank you. There are voices in academia, industry, and the general public advocating for limitations on AI research because of the risks it poses. Do you think that AI's current successes, because of its demise, hold on, do you think that AI's current successes be the cause of its demise? Over to you. I mean, I know that you have said that at DeepMind, you do that ethical analysis. You ask those moral and societal questions of dual use and all of those. But, you know, AI is available everywhere to everyone. Can we stop people using it? Can we ensure that that rigor of ethical assessment before the start?
Yeah, so I think it's a very good question, and I think with every sort of powerful sort of technology, there's an element of sort of using it responsibly, right? And I think. And I think we believe that there is sort of a role for sort of policymakers to think about what is appropriate use of AI, what is appropriate and safe use of AI systems. And I think we welcome that, because I mean, it's like with any powerful technology, there is an element of how should it be used, and it should be used in the service of humanity, right? It's what is the like. At the end of the day, we have to sort of still sort of think about the back to the mission statement. AI is not the end; it's a means to an end, right? And the end is basically to advance science and advance humanity, right? Advance humanity. That's basically the key part. So we need to make sure that we are developing all this very powerful technology, but just in the service of that end goal. And then there should be different tools, and policy should be framed in that way, so that it ensures that the AI systems and the AI research is aligned with the long-term benefit of humanity and our sort of way of life.
I do agree with you, but I also fear that in the way that we as a publishing house had to rapidly put together a policy when we received a paper with ChatGPT on as an author on the paper, and we realized that, you know, we don't have a policy on this. You know, there is a danger, I think, that the policymakers, the governors, might always be a step behind, and I think it's really important that we get on top of that in the way that we did with gene cloning. You know, society has to progress this before government does, I think.
Yeah, so I think that's absolutely sort of right. And I think the point to make is basically there is no time to lose, right? These are important sort of topics, and then the public discussion as well as the policy discussion around these topics is really important. And and we should not shy away from it. Right? These are so important topics that we can't just push them under the carpet and say, okay, well, it's hard and so on. These are hard things, but they need to be tackled and they need to be addressed.
Oh, yeah, I completely agree. And, Pushmeet, I'm looking at the time, and unfortunately, I know I have to stop because I could keep going for at least another hour. We still have lots of questions coming in. It has been my utmost pleasure to have this opportunity to be able to talk to you one-on-one. I'm sure you wouldn't have come if I'd asked on my own. So I have ransacked the talk a little bit because it's so fascinating to hear. I absolutely know our editorial board members are going to be very pleased to have been able to attend and hear your insights, and it's very thought-provoking. It's very exciting. It's an amazing area. I know there'll be more. I hope you come back one day to give us an update. But for now, I'm going to thank everyone for attending and listening, and hope you've enjoyed it as much as we have. And thank you again to our very special guest, Dr. Pushmeet Kohli. Thank you.
Thanks a lot.